Okay, welcome back to this new course, new paper. The paper name or title is Nuclear and Particle Physics, where we will be covering the nuclear and particle physics, nothing but nuclear and particle physics. Anyway, so this paper consists of two parts mainly. One is nuclear physics, and the second one is particle physics. And in the nuclear physics, of course, we will do or study the nucleus, about the nucleus, what are the different mechanisms or the structure, all those things. And in particle physics, we will study about particle. And the nuclear physics further divided into theoretical and experimental parts, where in theoretical parts we will be dealing with nuclear properties, nuclear models, radioactivity and nuclear reactions. In experimental we have different accelerators and different detectors. So first we will focus on the theoretical part, and in nuclear properties we will be considering the mass, size, spin, charge, etc., all those kind of things of the nucleus. Then we will go to the nuclear models. And in the nuclear models, we have different theoretical approaches or different models which explain the structure of the nucleus, like liquid drop model, shell model, etc. And the third one is the radioactivity, which is nothing but the alpha beta decay, why it is happening, when it is happening, all those kind of things we will study in this section. And we have the fourth one, nuclear reactions. And this one is nothing but the nuclear fission and fusion reactions, why this fission and fusion happens, what are the advantages and disadvantages of these reactions. Then we also cover the chain reaction, controllable and uncontrollable reactions, the nuclear reactors, etc. And in experimental setup or experimental part, we only consider detectors because it is only covered in your syllabus. Accelerators has nothing or not much in your syllabus, so it is not necessary. So it is only detectors we will be focusing for this paper. And we have the second part, that is the particle physics. We will be studying the fundamental properties of the elementary particles. Now, before moving to this nuclear physics, we need some introduction to this paper. So first we consider the atomic physics, which we already studied, where we deal with these atoms, the properties of atoms at different circumstances, where we discuss how the electrons are filled in different orbitals, different orbits, how they are in structure, and also how we can fill different electrons by using different principles like Aufbau principle, Hund's rule, maximum multiplicity, Pauli's exclusion principle, all those things. And then we also have different effects like Zeeman effect, Pascal-Beck effect, all those different effects associated with different atoms in electric and magnetic fields. All these things we already covered in atomic physics, or at least some basics of that we need to step into this nuclear physics. So I hope that you know that all those things, some basics of the atomic physics, because some of them we may need in this nuclear physics course or nuclear physics paper also. So let us consider the case when we are having two atoms when they are joined together, we can have a molecule. Okay, so this molecule, if we join n number of these molecules, then we have a chain of molecules which can form massive objects. So these massive objects can then produce or then turn into very large massive objects, and these objects are called as heavenly bodies. Okay, so when we when we deal with this gravity and astrophysics, all those studies which are related to these heavenly bodies. But we are not going to study these heavenly bodies. We are not going to study atoms. We are not going to study about molecules. We are not going to study about any other heavy bodies. But what we are going to do is we are going to look inside the atoms, what is happening inside the atoms. So in order to look inside, we need some thought of different ideas to know what is happening inside the atom. So one of this method is that bombarding different particles within the atom. So in this picture we can see that these alpha particles are hitting on these atoms. These alpha particles are hitting on this atom, and we study what is happening when these alpha particles hits on this atom, and when it come back, what will happen to these alpha particles. Similarly, we can use neutron, proton or any other particles and just bombard with these atoms and study the particles which are coming out, the scattered particles or the deflected particle or any kind of physical processes that happens. After that, we can analyze that result and we can predict some kind of results or observations about these atoms, or what is the mechanisms inside these atoms. So this alpha bombardment or the alpha scattering experiments were started by Giger and Marsden, and they were doing research under Rutherford as a collaborative research, but they were not looking for what we are interested in. They were just doing some experiment with alpha particle, just scattering that alpha particle by a thin film of gold and many other materials. So the schematic of their experiment is shown here. We have an alpha source here. This is our alpha source. I didn't include that picture, but there is an alpha source, and we have a plate, that is metal plate here. This is the metal plate, and then we have a detector also here. We have a detector. So these alpha particles, when they are ejected from the source, alpha source, they are coming and hitting on this metal surface. Okay, and it is observed that most of the alpha particles are passing through this, which are undeviated or slightly deviated. Most of them are very slightly deviated, and some of them are showing some kind of scattering, and some of them are deflected back like this. So these were the observation. Then they have changed the materials. What will happen if we change the material from gold to any other materials, or if we change the thickness of the material, what will happen? Such kind of studies were performed by Giger and Marsden, and they have published some good results. So in here, if these alpha particles are coming here and when they collide with zinc sulfide layer here, we have made this from zinc sulfide. So when they collide, they produce some sparks, or we can call them as scintillation, and that scintillation can be detected by this detector. And we also have a detector here to detect the scattered alpha particles. So this zinc sulfide is used to count the scintillation or the spark, to know how many alpha particles are coming back or back scattered from the metal surface. But Rutherford has some different idea. He was thinking about what exactly happening inside the metal, why this scattering is happening. So you can see from here there is another diagram which shows somewhat advanced setup for this gold metal alpha scattering experiment. We can have a alpha source here, alpha particle source, and these alpha particles are bombarded or inside on the metal, on the cold film, and most of them are undeflected. Most of the particles are undeflected, and some particles are scattered with some angle, and very few are deflected back, like this you can see. And you can use any other metal plate. Here we use thin gold foil. Gold is one of the best material to make it very thin. You can make very thin layer. That's why they have used the gold in here. So, and we are also having the circular fluorescent screen, and this fluorescent screen will also detect these alpha particles which are coming after this experiment, that after scattering and deflection. That can be counted or recorded at different angles. You can use detector here to see the scintillation, and we can observe where is the maximum alpha particles are coming, where is the minimum, all those things we can record. Okay, this is a diagrammatic representation of this gold foil experiment. So now what Rutherford was thinking was different, because he was more interested in the real mechanism that is happening inside the atom. He was not interested in what happens to the material, to the alpha scattering when the material thickness is increased or decreased, or the material change, or any such kind of physical changes on the material or the experimental setup. He was not thinking about that. He was thinking about the fundamental physics that is happening inside the atom. And here is the reason. If you consider an atom, which is, let's consider it is like a sphere, and we know if you are having a spherical charge distribution, you have the electric field variation, the electric field variation like this. Okay, so you are having your distance on the x-axis, and you are having electric field on the y-axis, and this is your electric field variation with distance. Okay, so let's say like this. So you will be having a maximum value at when r is equal to capital R, and this capital R is nothing but your radius of your spherical charge distribution. Okay, your maximum is at where the surface of at the surface of your spherical charge distribution. That is the maximum electric field that you can observe. And you can you also know that this will be proportional to R. That is, the electric field in this region will be proportional to R, and in this region it will be proportional to 1 by R square on this side. Okay. Now Rutherford was thinking, what will be the electric field if you are having a charge distribution of the size of an atom? That means if you are having a spherical charge distribution of an atomic size, then you can calculate what is the electric field that can be produced by such a charge distribution. And if you know the electric field, then you can calculate how much force it can exert on the alpha particle. So if you are having an electric field, let's say E at the surface, then you can have a force F equal to Q into E, where Q is the charge of alpha particle and E is the electric field that is created or produced by this spherical charge distribution. So this force will be exerted on the alpha particles when they come close to this charge distribution. But when he calculated, it is found that this electric field which is produced by this charge distribution of atomic size is not enough to deflect or scatter the alpha particles. The alpha particles are massive as compared to other particles like proton and neutron. So they cannot be that much easily scattered. So he was thinking, what will be the reason then? Then we again go to the electrodynamics. We can see your electric field is inversely proportional to the radius of the spherical distribution. Then if you are having a spherical charge distribution of very small radius, you will be having very strong electric field, and vice versa. Then he concluded that there can be a region where all the charges are concentrated, and this region is very, very small. And if you are having very small radius or your small charge distribution, then that can produce very huge electric field. When you are having huge electric field, that can produce very large force on the alpha particle, then only it can scatter. Then he proposed his idea like this, and it was like this. The center one is the charge distribution, which is the nucleus. Later we call it as nucleus, where these positive charges are concentrated, and the outer one is nothing but the electrons. So now we have a region which is very small, where the charges are concentrated, where you can have very large electric field, and if you have very large electric field in that region, we can have more force. Now if you are sending any alpha particle, let's say in this way, it will not be affected. In here it will not be affected, but in here it can be affected a little bit, and when you close further, it can affect a little bit more, like this. So that is the idea of Rutherford about the nucleus, and his predictions were very accurate. And he also calculated one important formula to calculate the number of scattered alpha particles, that is shown here. So from this you can see the number of alpha particles which are scattered is proportional to the total charge of nucleus, and it is inversely proportional to the sine, that is the fourth power of sine of theta by 2, and it is also inversely proportional to the kinetic energy square, that is square of this kinetic energy. So these are the three important factors we will be looking in this equation, and if it is that much important, we will derive this equation. I think we have to consider only these important facts. What are the three parameters, that is the three parameters which are important in this equation. So we will discuss how these parameters affect on the scattering, alpha scattering. We will be covering how the scattered alpha particle is going to be affected by the scattering angle, the incident alpha particles kinetic energy, and total charge of nucleus. First we will consider how the scattering angle is going to affect the number of scattered alpha particles, and from this expression we can see clearly that the number of alpha particles which are scattered is inversely proportional to the fourth power of sine of theta by 2, which means that if you are having an angle which is smaller, your sign value will be smaller, and your denominator will be smaller, which will leads to you more number of scattered alpha particles, which means that if you are having a scattering angle which is smaller, you will be having more number of alpha particles which are scattered. And if you increase this theta, then we will be having your denominator in your denominator we will be having maximum value, or your value will be increased, and the number of scattered alpha particles will be minimum. For example, in this case, when you are having alpha particles which are coming and hitting on this nucleus and coming back in the same direction, which are the back scattered alpha particles, in that case you will be having an angle of 180 degree. Okay. Now if you substitute this 180 degree in your equation, then you will be having sine of 90, which is the maximum value of the sine, and which will leads you the number of alpha particles scattered at that particular angle is will be minimum, because when you are substituting this 180, then you will be having in your denominator you will be having maximum, and the n of theta value will be minimum. So which means that the number of backscattered alpha particles will be very, very small, and the number of alpha particles which are scattered with the lower angle will be larger. So that's how the scattering angle affects on the number of alpha particles which are scattered. And now we will consider how the kinetic energy of the incident alpha particle is going to affect the number of alpha particles which are scattered. So let's say this is your nucleus, and now we will consider the alpha particles which are coming or approaching this nucleus like this. So let's say like this, it's going like this. Okay. Now we'll take another alpha particles which are coming in the same way, but which is having different kinetic energy, will produce its angle different. So it will be like this. Okay. How this is going to happen? That is our question. So this is having the first case is having an angle of theta, and the second one is having an angle of first one is angle of theta, and second one is having an angle of theta dash. Okay, so in this particular case we will be having a kinetic energy Ke1 and Ke2. So the yellow one, which are the alpha particles which are having kinetic energy of Ke2, and the blue one is having the alpha particles which are having kinetic energy of Ke1. Now if you, in this particular case, I can say Ke1 is larger than Ke2. So when your alpha particles are approaching this nucleus, the nucleus is having an impact on this alpha particle because of this electric field produced by the charge, this positive charge. So there will be a force which is QE that will be interacting with these incoming alpha particles. So if this incoming alpha particle is having more kinetic energy, that alpha particles will be affected less as compared to the alpha particles which are having low kinetic energy. So when this incident alpha particles having lower kinetic energy, it will be affected, or impact of on this those alpha particles will be large. It is like when you are having a very high speed motor vehicle or a car, then you cannot have that much impact on that particular vehicle. If you are moving it very slowly, then you can easily control it, or you can have any impact on that kind of situation. Okay, so when you are having kinetic energy which is larger, then the effect or impact of nucleus on that particular alpha particles will be smaller. So how this is, for example, if you are having a detector here at this angle of theta, okay, so you will be having n number of alpha particles which are scattered at an angle of theta, and if you increase then the alpha particles kinetic energy, then more number of alpha particles shifted into this this angle into theta dash, and your number of alpha particles which are scattered in theta angle, scattering angle theta will be decreased. Okay. So if you are increasing kinetic energy, the number of alpha particles which are scattered in a particular angle will be decreased. If you are decreasing kinetic energy, and your number of alpha particles will be increased for that particular angle. And third one is how these nuclear charge affect on this scattering. So in that case, suppose this is the nucleus, and if you are having a charge which is let's say charge is q. Let's take another one also for the same case. And this is having a charge q. This is having a charge q, and this is having a charge q plus let's say dq. Okay, so this one is having more charge as compared to this case. Now if you are having alpha particles which are coming and approaching this nucleus and scattered. Okay, so this is your angle theta, and you are having a dictator is at angle theta. Okay, this is the angle theta. So your angle, this detector is also at this angle theta. And in the same scenario, if you consider in the second case, okay, in that case you will be having with the same angle theta here. So what will happen? You will be having more alpha particles like this, more alpha particles which are undeflected or which are deflected very with very low scattering angle, very small scattering angle. So when you are having when you increase, in this case for example you are having a field like this, but when you are having more charge you will be having more field here. Okay, so more number of alpha particles will be having impact, and they can be scattered into that particular angle when you are increasing your charge. So when you are increasing your charge of the nuclear charge, or when you are changing your nucleus from a lower nucleus of having lower nuclear charge to a nucleus having higher nuclear charge, then more number of alpha particles get impacted and can be scattered into a particular angle. So the number of alpha particles will increase when you are having large value of nuclear charge. Okay. So in the size comparison, we have one size comparison here. Let's say for the case of hydrogen atom, we will be having atomic size which is equal to 50,000 times size of the nucleus, which means that if you consider 50,000 number of nucleus arranged in like this in a series way, 50,000 number of nucleus, then you will be having a size of atom. Okay. So if you consider that with this system, that is solar system equal to 6,000 sun size of the sun. So if you arrange 6,000 sun, you will get the solar system. If you arrange 50,000 of nucleus, then you will get atomic size. So it is the size of nucleus is that much very small. So it is in the order of 10 raised to minus 15, which is the femtometer or in femto range. So which means that it will be 0.000 times 10 to the power 14, that is 14 0, 10 to the power 15, that is 14 0 and 1. That is the size of your nucleus.